Thank you very much. Thank you for the invitation. The work I'm presenting today is a joint work with a few people, which I listed here. It all started actually, at least for me, as a piece of work I did with my student, Paul Wilson, who should also be in the audience. We worked on trying to extend the usual machine learning techniques to the setting of Boolean circuits, and we tried to use categorical semantics to achieve this goal. This was last year, and then we realized we were stumbling over something more fundamental there. And so this actually evolved into a more comprehensive framework for learning in different settings. And this is the second paper, which is listed here with more authors. So we joined forces with Bruno, Neil, and Geoff. And both works you can find available online. The second one is actually very recent. And what I'm going to present today is also part of ongoing work. So there is many things together, and they are still evolving right now. Um, the so as I said, the overall goal of this work I'm gonna show you is to develop categorical foundations for machine learning. Now, obviously, with machine learning, people mean very different things. So let me begin by trying to delimit a bit the scope of what we are interested in. Here I presented a typical machine learning scenario in a very simplified manner. Machine learning in this fashion usually takes place on a model, usually a neural network, which is made of nodes which are linked together by edges. This model, this network computes a certain function. So there are inputs coming in, they're computed through the network, and some outputs come out. But actually, the interesting aspect here is that there is additional information that is backpropagated. So there is this backward move within the network. The network is made of parameters. These are those that define the function that the network is actually computing. And the backpropagation, the action that it does, is to update these parameters. This is what usually is called training a network. So in what way these parameters are updated? Well, typically these networks, they need to perform certain tasks. For instance, here I put this little picture to exemplify that this network may, for instance, want to recognize pictures of cars in a more general picture. The network initially will may be very bad at this task, but backpropagation will update the parameters towards the goal of being more proficient at this task. For instance, more proficient at the task of recognizing cars in a given picture. So this is, for now, let's say, our running intuition. The thing is, obviously, as you know, machine learning has been exploding now for at least a decade, and there are many more ways of doing this kind of training, which takes place on a variety of different models. What I showed you previously was a picture of a neural network, but obviously we have many different architectures and many different variations, more and more sophisticated, of neural networks. For instance, we have recurrent neural networks. In this picture, we have generative adversarial networks in which there are multiple neural network architectures which interact with each other. And also we have models of learning which do not look at all like a neural network. For instance, the decision trees, which is what I depicted here. Moreover, within the same network architecture, there may be different ways of training them. For instance, instead of backpropagation being something simple, it may actually interact with the environment, as it happens, for instance, in reinforcement learning. So what we have here is actually a ever-growing family of machine learning techniques and models. And the general idea of this work is, how do we systematize this? How we capture, how we distill the fundamental mathematical structures that underpin learning? What do these models have in common? And can we characterize this common core in an algebraic manner? Now, the approach I'm going to take is the typical approach of people working with logic and semantics. So we're going to try to give rigorous semantic foundations for machine learning models and techniques. As usual, this is inspired by programming language theory, so it comes with the usual benefits in terms of abstraction. Namely, we're going to try to give characterizations of the aspects of learning which are independent of specific models and specific techniques. We want this to be uniform, so it should nicely encompass a variety of different examples. Think about the slides I just showed with many different ways of doing learning. And moreover, it should try to insert in the conversation about machine learning as many compositional methods as possible. I mean, this is what usually category theory, algebra, and logic is good at. Taking a subject which is usually tackled with non-compositional methods and trying to include some compositionality in it. Where by compositionality, I mean the usual way of analyzing a model exclusively in terms of their fundamental components. What is the more long-term payoff of this framework, supposing we're able to develop it? Well, I see this as an important stepping stone towards formal verification of machine learning, which is a very interesting topic, that is actually being worked on right now by a few people. Obviously, when you do formal verification, it's important to have semantics. We can see that in the example of programming language theory. So here we may opt to develop this kind of verification techniques once we have established this framework. Something else which I find intriguing is fostering cross-disciplinary exchanges. What I mean by that is that in the last few years, there have been many approaches to open systems in various areas of science and the compositional modeling of them using string diagrams. Think about quantum processes, think about concurrent systems, cyber physical systems, and so on. All these families of models have been analyzed more or less recently using category theory, semantics, string diagrams, and so on. So if we manage to do the same kind of framework for machine learning, I think that it can be the expectation of exchanging methodologies between these areas in a way that I think could be interesting. And finally, also from a more practical viewpoint, because the forms of analysis that we want to introduce are compositional, one may hope to devise new forms of reasoning about machine learning which are more scalable. Where scalability here really means to try to put compositionality at work and hopefully get more efficient algorithms for doing learning, for instance. So now that we have established, let's say, a general scope of what we want to do and what are the objectives, let me come back to the original example, and we can get started there. So in order to do that, I will need to make the original intuition that I gave you a bit more formal, a bit more precise. And this is actually what happens behind the scenes when I say that the neural network is trained. So not only we go from inputs to outputs, but these outputs are processed, if we like, by some error map, sometimes called also a loss function. This error map feeds some information to an optimizer. What is this information? The information is how the output is different from the intended output. So imagine, for instance, I insert this picture, the machine makes some mistakes in identifying the correct cars. Then the error function has these labels at disposal. At least this is what happens in supervised learning. And so it's possible to compare the output with the intended output, and this information is fed back. This information is then used by something called an optimizer, which is an engine, is an algorithm that will update the parameters according to this new information so that the machine can then perform better in the intended task. So this is a bit more precise picture of what's going on there, at least what is going on in what is called gradient-based learning, where the gradient here is just the machinery on which the optimizer is based. I had to introduce that because now we want to take a categorical look at this picture. So the plan is going to be to modularize gradient-based learning and interpret each of these modules that we identify in the learning process as something called a lens. So a lens is a categorical gadget. I will say in a moment what it means. And I claim we can understand the various components of the learning process uniformly as lenses. Learning then will be defined by lens composition. And this is the picture we will reach eventually. So this will be a string diagram in the category of lenses over a certain base category. And you can already start pattern matching, if you like, the various parts here with the various parts there. So we will have an input lens, model parameters, optimizer, model, error, the labels. All these things will be modeled as some sort of lenses, and they will all participate in devising the learning process. So in order to develop this picture, I will begin by analyzing the model. So for now, we strap all the dynamics that is behind the training process. So all the optimizer, error function, and so on. And we just exclusively focus on our neural network. In order to model this neural network categorically, first of all, we fix some ambient category. We want to work in the category of smooth. This category as you can think of the objects as being natural numbers, and then a morphism from n to m will be a smooth function, so a differentiable function from r of n to r of m, where r is the real numbers. A neural network, because a neural network computes a function over the reals, we can simply think of it as a morphism in this category. However, if we want to adequately model training over this network, we also have to account for two layers of structure. The first one will be parametricity. So we need to account for the fact that the network itself is based on some internal parameters. And secondly, we have to account for bidirectionality. With bidirectionality, what I mean is that not only we know that the network can, the information inside the network can flow from left to right, but it can also flow back right to left when it comes to updating the parameters according to training. Each of these layers will be taken care of, I would say, quite nicely by some categorical structure. So in order to account for bidirectionality, we start from the observation that smooth can be thought of as a so-called reverse derivative category. So reverse derivative categories are a categorical structure which has been introduced rather recently. This paper is from 2019, I think, in order to axiomatize the notion of derivative and differentiation in the context of category theory. Smooth is a reverse derivative category. What this means in concrete? It means that for any smooth function from A to B, I can define the reverse derivative of f, which has this notation R of f, which will be a function of type A times B to A. And this is how it's defined. So it sends x and y to the transpose of the Jacobian over f of x multiplied by y. So I'm not interested here in delving into the mathematics behind this formula, but if you want to have a running intuition, you can think of this as computing starting from a certain input, a change in an output, and gives me an approximation of the change I need in the input in order to account for that change in output. This is a bit the intuition behind this, and it makes sense when it comes to learning. This is actually a component of the gradient descent algorithm. What I want to emphasize here, however, is that once we work in a reverse derivative category, automatically the morphisms we are considering carry a lens structure. So now it comes the time to tell you abstractly what is a lens. First of all, if you already know lenses here, we are working, at least in the context of this talk, just with monomorphic lenses. So a lens is a morphism. A lens in the category C is a morphism in C from A to B, with two maps, a get map, which has the same type, and a put map, which has this other type. So you can immediately see how the types match the type of f and its reverse derivative. But what this means intuitively, the idea of a lens in general is that a lens is a gadget that allows you to manipulate a certain data structure, to access some data, and also to update data. It's quite common to encounter in the context of functional programming. It's also well known in the context of the theory of databases. And here we observe how it can be put at work also in the context of learning. What do lenses have to do with learning deep down? Well, you see that in lenses there are two flows of information, which are exemplified by this picture here on the right. So the get map we can think of as a forward action, and the put map we can think of as a backward action. So the idea is that the lens structure accounts for that same kind of bidirectionality that we can witness in the context of learning. There is the second layer we still need to account for, which is the layer of parametricity. And this is rather straightforward. We just apply a categorical construction, which we may call para. Instead of working in smooth, we are going to work in para-smooth. The only difference is that in para-smooth, any morphism from A to B is parametrized. And is morally actually a smooth a morphism from P times A to B, where P is some set of parameters, okay? So in this way, by operating this switch, our networks will always come with the corresponding parameters, and these parameters will be respected in a sense during composition, in the sense that when I compose to parameterize the morphisms, I carry on both the parameters of the first and the second one. So wrapping up what we've seen so far, a neural network will be simply a morphism in para, lens, or smooth, where para, lens are the two constructions we just saw, and they're actually functorial constructions. Now that we've seen the notion of a model, what kind of categorical semantics we can provide to it, I want to go to the optimizer. So here there are many more lenses we should define, but for time, for the sake of this talk, I think it's best to focus on what I think is most interesting here, which is how the optimizer becomes a lens. And we'll see that there is a quite interesting phenomenon here. When people think about these optimizers, they have in mind many different possible alternatives. There is the classic optimizer, stochastic gradient descent, but there are many variations like Nesterov, momentum, Adam, Adagrad. These are all variations of gradient descent that people have come up in the literature in machine learning in order to account for different properties they care for. For instance, properties in terms of convergence, in terms of the information you carry from one training step to the next one. Now, the nice thing here is that all these different optimizers can be understood uniformly as lenses. So it's not only gradient descent, but also all the other ones, we can actually reunite them under the umbrella of a common categorical structure. Let me first explain this for standard gradient descent. So remember, we have our model, which is a lens of this type. So it will have parameters, inputs, and outputs. The lens, the optimizer, as we know, changes the parameters. So it will be a lens of type para to para, where para is the set of parameters of our model. How are the get and the put map defined? Well, the get map is just the identity. In a sense, this optimizer is not doing anything forwardly, but the put map is giving me the action that I do backwards. And the action that it does, you may recognize this. This is simply the formula of gradient descent. So the first element gets updated based on a change, which is here for which here we adopt this notation. And this change may be amplified or diminished according to a certain constant, which is called a learning rate, which is this epsilon here. Okay, so this is how gradient descent also becomes a lens. And now we jump back to the full picture. So I explain what is GD here. I explain what is M. There are more components, obviously. So let me also record what was the original picture we wanted to give semantics to. So you can recognize the input becomes a state. So it becomes a diagram from nothing to A. The set of labels become a co-state, so it goes here and it communicates with the error lens, and the model parameters become another state. Okay. Something else to mention about this diagram is that these are all lenses. So this diagram lives in a category of lenses and is defined by lens composition. And when you read it, you have to think about information not flowing only in one direction, but because these are lenses, each defined with their own get and put map, information flows into different directions. For instance, this error here is communicating with these labels, but at the same time, in the training process, we'll communicate back to M some information which will be communicated to the optimizer in order to update the model parameters. So really here, the information, because we are working with lenses, flows into different directions. I just want to zoom in a particular aspect of this picture, which is how does training actually work? So the picture I provided you in the previous slide is somehow a static picture. I'm showing you how the different components are placed together. But training is somehow a dynamical process. So whenever we train a model, we feed some inputs, we adjust the parameters, then we provide more samples, we adjust the parameters, and so on. So how do we model this kind of iterative process with these diagrams in these semantics? Well, first of all, we can isolate what I like to call a train step. A train step is simply a sub-diagram of the diagram we saw in the previous slide, which contains the gradients, descent, the model, and the error function. And this train step is a lens because it's defined by lens composition. And it's interesting to see what the put map of this train step lens is. The put map is defined in this way. This is simply how lens composition work. So the put map of the train step will receive contributions from the get, the put maps, and so on of the various lenses which are involved. And the nice thing here is that you can actually compute how this put of train step becomes an algorithm starting from these smaller modules here. So in this definition, we really see the modularity of this approach at work. And if we want to train using this put map of train step, we can just draw, for instance, this string diagram where we put all of our samples of inputs and outputs on the right, and we do iterative refinements of our put train step map. And this intuitively will give us a trained neural network, one where the parameters get refined based on iterative steps of training. In the last few minutes, I want to discuss a bit how the approach generalizes to other contexts. Because so far, I only talked about supervised learning of neural networks using stochastic gradient descent. But what about other ways of doing the training? And what about other models? So now we'll briefly discuss that. I will focus on how do we change the optimizer and how do we change the model. I also mentioned the other parts in the very last slides. First of all, how do we vary the optimizer? So we have already seen gradient descent as a lens. As anticipated before, in the same way as we did gradient descent, we can do also other optimizers that appears in the literature. We can, for instance, formalize momentum, which is not here, but we have Nesterov momentum, we have Adagrad, we have Adam. What we did here is simply to transpose the formulas you find in the literature and verify that they actually are, that they actually can be stored as lenses. There is still something interesting here to notice, for instance, that whereas gradient descent is somehow a stateless operation, you see goes from para to para. For instance, for momentum, this is a stateful operation. We need to carry on memory of what we were doing in the previous step of the training. And this is also witnessed by the fact that whereas in the gradient descent, the get map is the identity, in natural momentum, for instance, the get map is not the identity. It does something depending on this gamma, which is what is called the momentum term. And if you're curious about how these lenses can be put at work in actual training context, we have an implementation which is available as a Python library at this link here. Okay.
Fabio, there's a question by Robin. What was the discarded information on the right of the train step map? That refers to the previous.
Oh yeah, sure. So this discard here is simply because by its type, the train step, the put of the train step also give us information about A. So it gives us not only some change in the parameters, but some change in the input. However, we do not use really this change in the input in the training process. So this is why it's discarded. Could you do something with this change in the input? Maybe, but so far this is how things are. Okay. Okay, resuming to where I was before, this is our, let's say, zoo of different optimizers that we explored. There are also more that you can find in the second paper I mentioned at the beginning. Another thing I want to mention about these optimizers is that not only they can be expressed as lenses, but the nice thing is that now that they're lenses, we can take advantage of all the operations the lenses have. For instance, we can think of composing them and coming up then with new optimization techniques. Or we can think of decomposing them. For instance, an interesting exercise I was trying to do with Paul earlier this week was how do we decompose Nesterov momentum? So we have a lens for momentum and a lens for Nesterov momentum, which is more complicated. Can we decompose Nesterov momentum in a momentum lens plus some kind of thing called an Nesterov lens, which I don't know what could be. So these are interesting exercises, I think, that gave us information on how actually the algebraic structures underpinning these various choices actually work. So we varied the optimizer. I just also want to mention how we varied the model. And the case study I will mention here is the one of Boolean circuits. So instead of training neural networks, what if we wanted to train Boolean circuits? So you may ask why Boolean circuits in particular? Well, there is a motivation there. The motivation comes from an area of research in machine learning called binarization. Binarization is a means to make a trained neural network more manageable from a computational viewpoint by extracting a corresponding Boolean circuit. The idea is that the Boolean circuit corresponding to the network will compute the same function, but in a coarser way by working on Booleans rather than real values. So the way this typically works is that first you train your network and then you extract the circuit. But one may also ask, what if instead you try to extract first and then train the Boolean circuits directly? This is an interesting question, I believe, because I would imagine that the training process for Boolean circuits is much simpler. You train on Boolean values rather than reals. So we came up with this question, and this generated another question. How do we actually define training on Boolean circuits? What it means to learn with Boolean circuits? And this is actually how we came up with the wall approach. But this in particular reminds us to the question what it means to learn with Boolean circuits, and the answer is provided by the picture I gave you before. So instead of working in the category of smooth functions, we can transfer the same diagram in the category of Boolean circuits. Of course, this doesn't go seamlessly. We need, for instance, to verify that Boolean circuits have a notion of reverse derivative, similarly to what the smooth functions have. What else does change? The model, obviously, the model will now be a Boolean circuit, and the optimizer we take. So for the optimizer, we came up with this notion called reverse derivative ascent, which is essentially gradient descent in the context of Boolean functions. Is very similar. We just don't have the learning rate here, and a few other parameters get simplified. Of all this approach, what I want to just focus on before concluding is the training step. So this, remember, was a diagram showing me how I train in successive iterations my model. This is how the put map for the train step looks like in the context of Boolean circuits. You may notice it's drastically simplified, as one would expect, with respect to the real case, the category of smooth functions. Another interesting and very important, I would say, thing to notice is that here, which is where most of the computation takes place, in the computing the reverse derivative of my model f. In here, the computation in the case of Boolean circuit can be made compositional. What does this mean? It means that we rely on the fact that Boolean circuits as a category can actually be presented by generators and relations. These generators are actually string diagrams. So we have a graphical syntax with which we can construct any Boolean circuit. And it turns out this reverse derivative here can be defined inductively on this circuit syntax. So in a way, it is defined compositionally, unlike, for instance, what happens with smooth functions. Now the question is, can we do the same for smooth function? Can we define reverse derivative compositionally with respect to neural network structure? I believe we could. It's just at this stage we still don't have the same understanding of neural networks in terms of generators and relations that we do for Boolean circuits. But this is one of the things I, for instance, would like to explore next. And just as for the smooth case we saw before, also in this case, there is an implementation which is available at this link. And this is also a bit more evolved. We have a benchmark test with some data sets. So we're in, if you go to this link, you can really get the feeling of what it means to learn with Boolean circuits. To conclude, I showed you this approach that we are investigating about giving a categorical semantics to machine learning, trying to encompass different contexts, different techniques, different models. What else are we doing at the moment, and what remains to be done? I already mentioned a few of that before. Other things I'm interested in is studying how we can vary the error length. The error length I had in my slides for the exposition of today is very simple. You just look at the difference between the output and the labels. But obviously out there are much more sophisticated techniques that people use, not only more sophisticated notion of loss, like cross entropy, but also reinforcement learning can be seen as a sophistication of the error length. You replace the error length with an actual context. And this is something I know that, for instance, Bruno and Neil and other people at Strathclyde are working on right now. I'm also interested in exploring training methods not based on gradient. So everything I showed you today is gradient-based computation, but I don't think there is anything, there is nothing essential to training that has to do with gradient. Gradient is just a means to do the training process, but in the spirit of this work, we should be able to abstract learning from what gradient is. For instance, there are out there things like evolutionary algorithms that are not based on gradients. And I would like to understand a bit better how we can abstract away from this particular way of training. There is the aspect of meta-learning. So meta-learning is an area of machine learning in which one explores how to actually train your training methods, in a sense. Can we do the same here? I think we do, for a very simple observation. If you notice, in this approach, models And optimizers are entities of the same kind. They are both lenses. So it's a natural question, just in the same way as we can train a lens as a model, can we train the lens optimizer? And this brings us to meta learning. So this is another venue we would like to explore. And finally, taking one step back, still in the perspective of trying to develop, let's say, a systematic foundation to learning, I would like to see if other ways of learning, other kind of systems, not necessarily neural networks, can be seen within the same perspective as we did here. What I'm referring to, any kind, said more very generically, any kind of open system which evolves through observation and through interaction with an environment. So this description applies to neural networks that get trained, but it also applies to Bayesian networks, for instance, that are updated according to belief revision, or dynamical systems that have an interaction with the environment that makes them evolve according to a certain trajectory, for instance. And also automata. You have automata learning, which is an area in which you refine your model based on the language that this automaton is supposed to recognize. So my idea is that all these various approaches, which are from very diverse research areas, could actually be seen uniformly within this perspective. And this is, let's say, my longer term goal, to try to develop this systematic view. If you want to know more about this, as I mentioned before, there are these two papers, and these are also the links to the code. And this is all I wanted to say, and I can now listen to questions. Thank you very much.
Thank you very much, Fabio. Thanks for this very nice talk. There were some questions towards the end that I skipped, so let me just stop the recording.